Hello and welcome to all students. In this lecture, we will learn about limit of real valued functions. Now we see the outline of our lecture. First, we see definition of limit of a function. Second is epsilon delta definition of limit of function. Third is limit of some standard function. And finally, we see examples on limits of functions. Now see the definition of limit of function. We see the formal definition. Let f of x be any real valued function. Let L and A be any two real numbers. The limit of function f of x is said to be L as x tends to A if the part after the if is very important. If whenever values of x approaches to A, then the values of function f of x must approaches to L. So see once again, if whenever the values of x approaches to A, then the values of function f of x must approaches to L. So this formal definition is the basic of limit of a function. So whenever we say that limit of function is L as x tends to A, this means that whenever the values of x approaches to A, then values of f of x must approaches to L. Okay, must approaches to L. So we note some points. This limit is denoted by limit of f of x equal to L as x tends to A. This is the notation for denoting limit of a function. Okay, now next see here values of variable x approaches to A. Values of variable x approaches to A but not touches to A. That is very important. Values of x approaching to A but they are not touching to A. Next is here whenever distance between values of x and A becomes smaller and smaller, then the distance between values of f of x and L becomes smaller and smaller. So see here, this is the basic of limit of a function, and this slide is the soul of concept of limit of function. Okay, so now we go to the next definition of limit of function. We call it is epsilon delta definition of limit of function. So we define this definition. Let f of x be any real valued function. Let A and L be any two real numbers. We say that limit of function f of x is L as x tends to A if the part which coming after if is very important. So what is that part? If for any given epsilon greater than 0, epsilon is very small, there exists a delta greater than 0, so delta is also very small, such that whenever mod of x minus a is greater than 0 and less than delta, this implies mod of f of x minus L is less than epsilon. Now see here, this is again a definition of limit of function. So what we have defined in the previous slide, the same thing we are putting here in terms of just notation, So here also have to define limit of a function L as x tends to A. So when we say that, so see here, this term geometrically, what is the meaning of this term? So geometrically, mod of x minus A is nothing but distance between x and A. And here we are saying that distance between x and A is greater than 0, means x is very okay, and again we are saying that this distance is less than delta, but delta is a very small quantity, therefore we say that distance between x and A is very small. Distance between x and a is very small. Means x is very close to a, but x is not equal to a. Means values of x approaching to a but not touches to a. That is very important. And whenever this happens, if this happens, this term, what is this thing? Uh, this is mod of f of x minus L is less than epsilon. So geometrically here the mod of f of x minus L is also represents a distance between f of x and L, and see the distance between f of x and L is less than epsilon. Less than epsilon, here epsilon is a very small positive quantity. Therefore here also we say that values of f of x, they are very close to L. Okay, so whenever values of x are very close to a, then values of f of x are very close to L. Okay, that's it. That is our basic definition of limit of a function. Okay, so we note some points here. Here we observe that L is called the limit of function f of x as x tends to a. This limit is denoted by limit of f of x equal to L as x tends to a, as we seen in the last previous slide. And geometrical meaning. So just I have explained here the geometrical meaning. So what is geometrically? We say that the limiting position of function f of x is L as x approaches to a if whenever distance between x and a is very small, then the distance between f of x and L is also very small. So it is about the definition of limit of function. So x is a real number, x is a real variable, and a is a real number. So x approaching to a means x may approach from the left hand side of a, or x may approach from the right hand side of a. So doesn't matter. Okay, so we will see afterwards if x approaches to a from the left hand side, and if x approaches to a from the right hand side, then we have different notation for a limit, and we call so we will see afterwards. Okay, next is evaluation of limit using epsilon delta definition of limit. So let us take some problems based on limit of a function by using epsilon delta definition. So first question is show that a limit of x square plus 7x equal to 44 as x tends to 4. Show that this thing. So let us write the answer of this question. So very simple. By using epsilon delta definition, we will prove that the limit of this function is 44 as x tends to 4. So here we show that we have to show this limit, means we have to show the, by definition of epsilon delta definition of the limit of a function, we show this thing for any given epsilon greater than 0, however small, there exists a delta greater than 0 such that, so this is the notation for such that whenever the, now I'm not whenever, so this part I'm not reading like mod of x minus 4 greater than 0 less than delta. So I will say geometrically whenever distance between x and 4 is greater than 0 and less than delta, this must imply distance between, so geometrically this mod function represents the distance. Therefore distance between function x square plus 7x and number 44 is less than epsilon. That we have to show here. Okay, so consider this part first. X square mod of x square plus 7x minus 44. So consider this thing, x square plus 7x minus 44 modulus, but this is quadratic polynomial, and this quadratic polynomial, therefore it has two factors. So I will write these two factors in modulus. First factor is x plus 11, second factor is x minus 4. and by property of modulus we can separate this modulus to each factor. So this is mod of x plus 11 into mod of x minus 4. So let us call it is first statement. Now choose delta less than 1. Now why we are choosing delta less than 1? We have to show that there exists some delta. We satisfy this condition. We have to show that there exists some delta. We satisfy this condition. Yes, there is a delta, but let us choose for our convenience. Let us choose delta to be less than 1. So this will implies this thing. Mod of x minus 4 is less than delta. This is what we have. But delta is less than 1, therefore this again implies mod of x minus 4 is less than 1. Okay, so value of this distance mod of x minus 4 is less than 1, and this implies by property of modulus again x minus 4 will be greater than minus 1 and less than 1, and this implies uh, value of x is greater than 3 less than 5. So just add a 4 in each term. Just add 4 in each term. Here 4, add 4, we add here in this term, add 4, and we add 4 here also, so that you will get this thing. Again add 11 in each term and then see what we get. So here if we add 11 it is 14, if we add 11 here it is x plus 11, and add 11 here it is 16. Okay, so inequality remains as it is. Now so this implies that modulus value of x plus 11 is less than 16. Okay, now from equation 1 we have this thing. So this is our equation 1, but now this quantity is less than 16 and this quantity is less than delta. So see here whole quantity will be less than 16 into delta, and this implies now finally the term x square mod of x square plus 7x minus 44 is less than 16 into delta. So what will be the choice? What will be the choice of our delta so that this condition will be true? So our choice of delta must be choose delta equal to epsilon upon 16. So if I choose delta like this, then what we have is x square mod of x square plus 7x minus 44 will be less than epsilon, and that is what we want to show you. So there exists delta. So for given epsilon, okay, here we show that for any given epsilon is given to you, and we have to show that there exists here, there exists delta greater than 0. So this is the existence of delta. You give me any epsilon greater than 0, I have delta greater than 0. Like this we satisfy this condition. Okay, so in this way we show we prove that the limit of x squared plus 7x is 44 when x tends to 4. Okay, now see the next question. Show that limit of a function square root of x plus 19 as x tends to 6 is equal to 5. Okay, write down answer. Here we show that for any given epsilon greater than 0, epsilon is given to you, any epsilon, however small, there exists a delta greater than 0 such that whenever distance between x and 6 is greater than 0 and less than delta, this must implies distance between square root x plus 19 minus 5 is less than epsilon. Now consider the calculation related this. Consider first term this. Here it is first term. Okay. This term is modulus of root of x plus 19 minus 5, and it is equal to, we just rationalize this term. Rationalize means divide by a root of x plus 19 plus 5 and multiply by root of x plus 19 plus 5. So this process is called as a rationalization process, and take a multiplication of these two terms, and the multiplication of these two terms is x plus 19 minus 25. Okay, this is like a square minus b square equal to a plus b into a minus b. Okay, factorization, and the denominator is as it is. Now calculation for numerator is x minus 6, denominator is again as it is. Okay, now see, thus we have this thing, mod of root x plus 19 minus 5 equal to x minus 6 divided by square root x plus 19 plus 5. Let us take delta less than 1 for our convenience. Let us take a delta less than 1, and this will imply mod of x minus 6 is less than 1, and this implies again x by property of modulus x minus 6 is greater than minus 1 and less than 1. This implies x is greater than 5, x is less than 5, and finally we will show that this thing root 24 plus 5 is less than square root x plus 19 plus 5. It is very simple to show that. Just what we have to do, what are the steps? I neglected the steps here. So first step is just add 19 in each term, then take a square root, okay, and then add 5 in each term. So these are the steps. So if you follow these steps, you will get this step. Okay, so now if I take a reciprocal, inequalities will get changed. So this term is less than this term, and if we take a reciprocal, then inequality will get changed, and 1 upon square root x plus 19 plus 5 will be less than 1 upon square root 24 plus 5. Now from equation 1, this is our equation 1, and see here the term mod of x minus 6 is less than delta, that is given to you, and this term below which is less than 1 upon square root 24 plus 5. So what will be the choice of our delta? So choose delta to be epsilon into, if I choose delta equal to epsilon into square root 24 plus 5, just put the value of this delta here, you will get this thing, mod of square root x plus 19 minus 5 is less than epsilon, means distance between function root x plus 5 x plus 19 and the number 5 is less than epsilon. Okay, so this is our this is the end of our problem. Now see, next, one-sided limit. So as we discussed earlier, in the limit when x tends to, when we say x tends to a, x may tends to a from the left hand side of a or from the right hand side of a. When x approaches to a from left side of a, then it is called as a left hand side limit. Okay, so here function f of x is said to have a left hand limit L as x tends to real number a if for any given epsilon greater than 0, however small, there exists delta greater than 0, very small, such that whenever x is greater than a minus delta and less than a, this must imply modulus of f of x minus L is less than epsilon. So this is the definition of left hand side limit of a function. So here L is called as left hand side limit of function f of x when x tends to a. So in this case, x tending to a from the left hand side of a. So if x is at the left hand side of a, then obviously on the real line if we see, x must be less than a, and as x is very close to a, so x lies between a minus delta and a. Here delta is a very small number, Therefore a minus delta is a number which is less than a, so x lies between a minus delta and a. So here x is approaching to a from the left side of a. So whenever this happens, this must imply distance between values of function f of x and L is very small. Okay, so we here the value of x approaching to a from left side of a, this left hand limit of function f of x is denoted by limit of f of x is equal to L as x tends to a minus. The meaning of x tends to a minus is x approaching to a from the left side of a. Okay, now one-sided limit, right hand side limit. So as we defined left hand side limit, similarly we have to define a right hand side limit. The function f of x is said to have a right hand limit L as x tends to a, as x tends to real number a, if for any given epsilon greater than 0, epsilon is however small, there exists a positive number delta which is greater than 0, very small, delta is also very small, such that whenever x is greater than a, less than a plus delta, this implies modulus of f of x minus L is less than epsilon. So see here, L is a right hand limit of function f of x as x tends to a. So in this case, x tending to a, or we say that x approaching to a from the right hand side of a, and as here delta is a very small quantity, therefore a plus delta, small positive quantity, therefore a plus delta is greater than a, and x lies between a and a plus delta. So this means that x is very close to a, but x is on the right hand side of a, means values of x approaching to a from the right hand side of a, then the distance between function f of x and number L is very small. This distance is less than epsilon, and epsilon is very small, so this distance is very small, means values of f of x approaches to L. So this is the definition of right hand side limit, and here the value of x approaches to a from right side of a. This left hand limit of function f of x is denoted by this notation: limit f of x is equal to L as x tends to a plus. X tends to a plus means x approaching to a from the right hand side of a on the real line. Okay, now see the left hand limit and right hand limit. We have to write one note. So if both left hand limit and right hand limit of a function f of x as x tends to a exist and both are equal to L, then the value of a function, then the limit of a function exists and is equal to L. So okay, so whenever both the limits exist and they are equal, means both left hand side limit and right hand side limit exist, and if they are equal, then the limit of that function exists and that limit is equal to the equal value L. Okay, that is if limit of f of x extends to a minus equal to L and limit of f of x extends to a plus equal to L, then limit of function f of x extends to a equal to L. When left hand side limit is L, right hand side limit is L, then the limit of that function as extends to a is L. Now see the example. Consider the function modulus of x, y equal to modulus of x for all x belongs to R, and we know the graph of mod function. Okay, now we are well aware about the graph of this mod function, mod of x. So see here in the graph, when x approaching when x approaching to 0 from the left side of 0, in this case the values of function, they are also approaching to 0. Okay, so in this case we say that limiting position of function mod x is 0 when x approaching to 0 from the left hand side of 0. So see here, limit of mod x is 0 when x tends to 0 minus. So this is the left hand limit of mod x function, and that left hand limit is 0. Similarly we see here, when x approaches to 0 from the right hand side of 0, in this case the values of function, approaches to 0. Okay, so it is called as right hand limit. It is called as the right hand limit of modulus of x. The limit of modulus of x is 0 when x tends to 0 from the right hand side of 0. So here the value of left hand limit and value of right hand limit is 0, it is equal to 0, and therefore the value of limit of mod x as extends to 0 is 0. So this is the simple example of function. This is simple example of limit of function. Now we see the limit at infinity and infinite limit. Limit at plus infinity. A function f of x is said to have limit L as x tends to infinity if given epsilon greater than 0, however small, there exists a big number m greater than 0, such that whenever x is greater than m, this must implies mod of f of x minus L is less than epsilon. Now what is the meaning of this definition, limit at plus infinity? When we say function f of x has limit L when x tends to infinity. So here we have defined that thing. So x tends to infinity means x becomes larger and larger. The meaning of x tends to infinity is x becomes larger. So limit of f of x is L means functional values of function f of x approaches to L when x becomes larger and larger. So when we say this thing, if given epsilon greater than 0, however small, there exists a big number m greater than 0, such that whenever x is greater than that big number, means x is also very large. That means whenever x becomes larger and larger, this implies that distance between function f of x and L is very small. Okay, so this limit is denoted by limit of f of x equal to L when x tends to infinity. So here we say that limit of function f of x is L as x tends to infinity means whenever x becomes larger and larger, the values of function f of x becomes close to L. Okay, approaches to L. This means whenever x becomes larger and larger, the value of f of x approaches to L. This means whenever x becomes larger and larger, value of function f of x approaches to a real number n. Okay, and see the example of this type of limit. The limit of function x into sin 1 by x is 1 when x tends to infinity. Okay, now see the limit at minus infinity. A function f of x is said to have limit L as x tends to minus infinity if for any given epsilon greater than 0, however small, there exists a big number m greater than 0 such that whenever x is less than minus m, this must implies mod of f of x minus L is less than epsilon. So see here, this means that whenever we say that f of x, limit of f of x is L as x tends to minus infinity if whenever x becomes smaller and smaller, as m is very big number, minus m is very small number, and x is smaller than, x is less than that very small number, therefore x, so we say that whenever x becomes smaller and smaller, the distance between values of function f of x and L, they are also very small. So this limit is denoted by notation limit of f of x is equal to L when x tends to minus infinity. The meaning of this thing is again, when x becomes smaller and smaller, values of f of x approaches to L. This means whenever x becomes smaller and smaller, the values of function f of x approaches to a real number n. The example of such a type of limit is limit of function e raised to x is 0 when x approaches to minus infinity. In the graph of function e raised to the power x, we have seen the values, the functional values of e raised to x approaches to 0 when x becomes smaller and smaller. So see the graph of function e raised to the power x, you will observe that. Now infinite limit, limit at plus infinity. Let us define a function f of x is said to have limit plus infinity as x tends to a, as x tends to a real number a if the part coming after it is very important. If for any given big real number k greater than 0, there exists delta greater than 0, very small, delta is very small, such that whenever mod of x minus a is greater than 0 and less than delta, this must implies values of f of x greater than k. So see here, we observe here, this means whenever distance between values of x and a becomes smaller and smaller, the values of f of x are greater than k. What is k? K is very big number, means values of f of x becomes larger and larger. Okay, so this limit is denoted by limit of f of x equal to plus infinity x tends to a. Here again, this means whenever x approaches to a real number a, then values of function f of x becomes larger and larger. That is very important. See the one example of such type of limit. The limit of tan x function is plus infinity when x approaches to pi by 2. Now limit at minus infinity. A function f of x is said to have limit minus infinity as x tends to a real number a if for any given big real number k greater than 0, there exists delta greater than 0, delta is very small, such that whenever, this again, whenever mod of x minus a is greater than 0 less than delta, and this implies f of x, values of function f of x, they are less than minus k. This means whenever distance between x and a is very small, or we can say whenever x approaches to a, the values of function f of x, they are less than minus k, means they are. But what is minus k is as k is a very big number, positive big number, then minus k will be very small number. Okay, there, and values of f of x, they are less than this small number. So we again see here, whenever distance between x and a is very small, the values of f of x, they become smaller and smaller. So this limit is denoted by limit of f of x tends to a equal to minus infinity. This means that whenever x approaches to a real number a, then values of function f of x becomes smaller and smaller. For example, see here, the limit of tan x function when x approaching to minus pi by 2 is minus infinity. So you will observe that from from the graph of tan x function. Now let us see one question. Show that limit of 1 upon x function, limit of 1 upon x when x tends to 0 plus is equal to infinity, and the limit of 1 upon x as x tends to minus infinity is equal to minus infinity. And what can you say about limit of 1 upon x tends to 0? So all these things you can observe from the graph of 1 upon x function. Okay, but we will solve this problem here. So answer, we write part 1. In part 1 we show that limit of 1 upon x tends to 0 plus is equal to infinity. That is, we show that this is the right hand limit of function 1 upon x. That is, we show that for any given big number m greater than 0, there exists delta greater than 0, such that whenever x is greater than 0 and less than delta, means x approaching to 0 from the right hand side of 0, this must implies 1 upon x is greater than m. Values of 1 upon x becomes larger and larger as m is very large number. Okay, so how to show? See here, consider as given x is less than delta, therefore if I take a reciprocal, then 1 upon inequality will get changed. 1 upon x will be greater than 1 upon delta, and therefore we choose delta equal to 1 upon m. If I choose delta equal to 1 upon m, then what we'll have is 1 upon x is greater than m. So there exists delta. We can choose delta, means there exists delta. That we have to show. So for any given epsilon greater than 0, we can find a delta such that delta and delta. Okay. So for any big number m, for any given big number m, we can find a delta so that this condition is satisfied. Okay, so see here, this condition is satisfied. So this implies limit of 1 upon x tends to 0 plus is equal to infinity. Now consider the second part. In second part we show that limit of 1 upon x tends to 0 minus is equal to minus infinity. That is, we show that for any given big number m greater than 0, there exists delta greater than 0. Delta is very small, such that whenever x is greater than minus delta and less than 0, this must implies 1 upon x is less than minus m. That means whenever x approaches to 0 from the left hand side of 0, the values of 1 upon x must be less than minus m, means values of 1 upon x become smaller and smaller. Okay, now consider the part minus delta, this part minus delta is less than x. So if I take reciprocal, inequality will get changed and minus 1 upon delta becomes greater than 1 upon x. That is 1 upon x is less than minus 1 upon delta. Therefore we choose delta equal to 1 upon m. If I choose delta like this, then 1 upon x becomes less than minus m, and this is our aim to show that. Okay, the limit of 1 upon x is limit of 1 upon x tends to 0 minus is equal to minus infinity. So in say third part from 1 and 2, we observe that a left hand limit of function 1 upon x and right hand limit of function 1 upon x, they are not same. Therefore this shows that the limit 1 upon x tends to 0 does not exist. Okay, so this is the last problem of our lecture, and we stop here. Thank you for paying attention.